Hello and welcome. Today, we're going to pull back the curtain on the invisible world of the air all around us. We're going to explore the science and, more importantly, the tools that engineers use to take that air and make our indoor spaces just perfectly comfortable. So, let's jump right in.
You know exactly what I'm talking about, right? It's freezing outside, you crank up the heat inside, and almost instantly your skin feels tight, maybe your throat gets a little scratchy. It's a super common thing, and it all boils down to the properties of the air itself. We're about to figure out exactly why that happens, and, even better, how we can fix it.
So the solution to our dry air problem has this kind of fancy name, psychrometry. But hey, don't let that technical term throw you off. All it really is the science of moist air. Think of it as the playbook engineers use to control temperature and moisture to create that perfect indoor feeling.
Okay, so before we can start changing the air, we need a way to describe it. We need a common language. It's like learning a few key words, and once you get those down, everything else just starts to make sense. First up is the one we all know and love, dry bulb temperature. Seriously, this is just the air temperature you see on a weather app or your home thermostat. It's our starting point. Just how hot or cold is the air. Simple as that. Next up, we have the humidity ratio. Now this one is really important. It measures the actual amount of water vapor, the real moisture, that's mixed into a chunk of dry air. This isn't a percentage, it's a direct measurement of the stuff that's in the air.
And that leads us right to relative humidity, the one you always hear about on the news. The key word here is relative. It's a percentage that tells you how full of moisture the air is compared to the absolute maximum it could hold at that specific temperature. And this is the secret to our dry winter air problem. See, when you take cold air from outside and heat it up, its ability to hold water just explodes. So that same little bit of moisture now feels like a tiny drop in a huge bucket. The relative humidity just plummets, and that's what makes the air feel so incredibly dry.
Now, here's where it gets really powerful. These three things, temperature, humidity ratio, and relative humidity, they aren't just separate ideas. They're all locked together by the laws of physics. What that means is, if you know any two of them, you can always figure out the third. This is what gives us the power to really truly understand the condition of the air.
So, how in the world do we juggle all these properties without getting tangled up in a bunch of messy equations? Well, we use this amazing tool called a psychrometric chart. And honestly, the best way to think about it is it's a map. It's a map for the properties of air.
Okay, I know. You look at this thing and it's just a wild web of lines going everywhere. It can look pretty intimidating, but I promise you, once you learn how to read it, this becomes one of the most useful tools you can imagine. We're going to make it simple together.
Let's start with the basics. Look at the horizontal line at the bottom. That's our dry bulb temperature. As you move from left to right along that line, the air gets warmer. That's our first coordinate on the map. Easy enough?
Now look over to the vertical axis on the right side. That's our humidity ratio, the actual amount of water in the air. So as you go up the chart, the air has more and more moisture in it. So moving right means hotter, and moving up means more humid. See, we're already reading it.
And finally, you see all those big swooping curves? Those are the lines for relative humidity. That far left edge, that's the 100% line. That's when the air is totally saturated and can't hold another drop. As the curves sweep down and to the right, the percentage goes down. And just like that, with those three things, you now know the basics of how to read this map.
All right, so now that we can read our map, let's actually use it for something. We can actually trace the journey of an air conditioning process, like taking that cold, dry winter air and making it warm and comfortable.
So here's our mission. We're starting at what we'll call State 1. That's the cold, dry air outside. And our destination is State 2, the warm, cozy, and comfortable air we want inside. The HVAC system is basically the vehicle that takes us on this journey from one state to the other.
And look, on our map, we can see this journey as a clear path. To get from State 1 to State 2, we have to move to the right, which means we're adding heat, and we have to move up, which means we're adding moisture. This whole complicated process just became a simple, straight line on our map.
Now, underneath this simple visual path, there's some real physics at work. The whole thing is governed by the conservation of energy. This equation here is just the official way of saying something we already know. You can't create or destroy energy. The energy of the air coming in, plus any energy we add, has to equal the energy of the air going out.
All right, theory is great, but let's see how this stuff actually works in the real world. We're going to run through a quick example to see how an engineer uses this map to design a real heating system for a building. It's a pretty straightforward three-step plan. First, we define what we're starting with and where we want to end up. Second, we find those two spots on our psychrometric chart and draw the line. And third, we use the values from the chart to calculate exactly how much energy we're going to need. Let's do it.
So here's our situation. We've got outside air coming into our system, and it is a chilly 5 degrees Celsius and a very, very dry 20% relative humidity. We can find that exact spot on our chart. We just go to 5 degrees on the bottom and move up until we hit that 20% curve. That's state 1.
And our destination? A nice and comfy 25 degrees Celsius at 50% relative humidity. That's the dream, right? So we find that spot on the chart too. And there it is, state 2. Now we have our start point and we have our end point. We have our path.
So now, all we have to do is read the properties for state 1 and state 2 right off the chart, plug them into our energy equation, and boom, we get our answer. The heating system needs to have a capacity of 43.6 kilowatts. That one number tells an engineer exactly what size equipment they need to get the job done.
And that's really the main takeaway here. We took a complicated problem with all these invisible properties of air, and we used our map, the psychrometric chart, to turn it into a clear, visual journey that gave us a precise, solvable engineering answer. How cool is that?
So we have pretty much mastered how to make a space comfortable during a cold, dry winter. But what about the exact opposite problem? What does our path on the map look like when we need to take hot, sticky summer air and cool it down? Well, that is a fantastic question for next time. Thanks for hanging out with me on this one.